Good day, dear students. Down, please. Today is our lecture with topic magnetic fields. Again, this lecture have the plan, which have 4 questions. First question: in brief history of magnetism. Second question: magnetic poles. Third question: magnetic fields. And fourth question: magnetic force on a current carries conducting. Please read into your copybooks. Okay. And new words in our lecture. New words. Please write into your copybooks and repeat after me. Okay? Uniform magnetic fields.
Uniform magnetic fields.
Однородное магнитное поле. Pole.
Pole.
Полюс. Permanent magnet.
Permanent magnet.
Постоянный магнит. Bar magnet.
Bar magnet.
Это полосовой магнит. Okay. Surround.
Surround.
Это окружение. Okay. Компас.
Compass.
Это компас. And needle.
Needle.
Это игла. Iron fillings.
Iron fillings.
Это железные опилки. Attract.
Attract.
Это притяжение. И последнее слово у нас repel.
Repel.
Это отталкивание. Окей. New words, right, in your vocabulary books. Did you record? Okay. Go to the first question. 13th century BC, Chinese is using a compass. They used iron, Arabic or Indian region in the tree. What is the compass? Okay, Nazgul.
It is compass. It's a professional device. This is have 4 directions. They are south, north, east, and west. South is processed 0 degree. North is processed 180 degree, and west is 270 degree, and east is 360 degree, and its compass was first in China, and it have a dial and a needle, and they have different types. They are non-magnetic compass, magnetic compass, and electric compass, and different. Magnetic compass, it is most popular compass type, and they have 2 directions, south and north.
Okay, thank you, Nazgul. Down, please. Okay, 800 BC, Greeks discovered magnetite ferrum 304 attacked piece of iron. Okay. 1618, Pierre de Maricourt found that the direction of a needle near a spherical natural magnet formed lines that encircle the sphere. The lines also passes through 2-point diameter opposition to each other. He called the point poles. What is magnet?
May I?
Okay.
Magnet Magnet is a material or object that produces invisible magnetic field which attract that allows ferromagnetic materials. Every magnet has two poles. These are north pole and a south poles. There are two sets of north and south poles on Earth. The magnetic poles and geographic poles. They are different. Two types of magnets, permanent magnet and electromagnets. Permanent magnets produce of electric field. Electromagnets need electricity to work.
Okay, very well. Thank you. Next presentation, and 1600. William Gilbert was an English physicist. Expanded experiments with magnetism to a variety of materials. He is suggested that Earth itself was a large permanent magnet. This is like Earth. Earth is large permanent magnet. Okay?
The Earth is a magnetic body around which a magnetic field is formed. Scientists believe that it is caused by current, everything to the relation and of the course of the substance and of the Earth. Due to the magnetic field, the Earth is protected from the particles, and these particles do not directly for our planet, and this we can see our Earth this place.
Okay, thank you. Please, sit down, please. Next presentation, 1819. Hans Christian Ørsted was a Danish physicist. He has discovered the relation between electricity and magnetism, and he has discovered what the conductor with no current, so magnet needle, no tone, but conductor with electric current, near conductor magnetic needs, around tone, near axis. And look at the picture. This is switch, close and open. Close switch, compass needle, turned. Open switch, compass needle, no turned. Okay. 18th, 12th, yes. Faraday and Henry. They discovered future connector between electricity and magnetism. Maxwell was a famous Great England physics, Chinese between electric field produced a magnetic field. And you look at the blackboard, you see at the, what is it?
Northern Lights.
Okay.
Northern Lights. The glow of the particles of the atmosphere under the influence of the charged particles of the solar wind. Northern Lights type of A floating gas turbine power plant developed in 1916 by the Turkey Central Decision and built as a turbine. The Northern Lights actually the result of collision between gaseous particles from the Earth's atmosphere. The most common auroral color, the pale yellowish green, in produced by oxygen molecules located about 60 miles above the minute.
Okay, thank you, Julius. Okay, what is beautiful picture? Yes?
Yes.
Okay. And go to the second question, our plan, our lecture, and magnetic poles. Every magnet, regardless of its shape, has two poles, colored and north pole and south pole. Okay. Unlike poles attract each other. Example, north pole and south pole attract each other, and south pole and north pole attract each other too. Okay. Like poles, example, north, or south, repel each other. North, what repel, and south, repel each other too. Okay. The poles received their names due to the way magnet behaved in the Earth's magnetic field. You know, Earth have two poles, north pole and south pole. This is geographic pole. Yes? Okay. Earth have magnetic poles, but north magnetic poles are located near south geographic pole, and north geographic pole located south magnetic pole. Okay? Next two. The force between two poles varies and the inverse square in the distance between them. In other words, magnetic poles are always found in pairs. If we give bar magnet and divided two parts, we take two magnet, okay, and each other, south pole and north pole, south pole and north pole, because magnetic lines no divided. Okay. Go to the 3 question and our lecture. Magnetic fields. You know, an electric field surrounds any electric change. The region of space surrounding any moving electric charge also contains a magnetic field. A magnetic field also surrounds a magnetic substance, take up a permanent magnet. Do you understand me?
Yes.
Okay. Magnetic field is a physical quantity. Is vector quantity. Okay. Symbolized by V. Okay. Direction is given by the direction north pole of a compass needle point in that location. Magnetic field lines can be used to show how the field lines are traced it by a compass would look. The compass can be used to track the field lines. The lines outside the magnet point from the North Pole to the South Pole. Okay, North Pole to the South Pole. And magnetic line, no cross. Okay. Next, look at the picture. You see three pictures. Okay? Three cases. First case, permanent magnet, which North Pole and South Pole. And we see magnetic lines. Okay. Second case, two permanent magnet and unlike South Pole and North Pole. This is magnetic lines is attract each other magnet. Okay. And third case, north and north is two permanent magnet, and we show repel each other. Okay. Okay. Iron fields are used to show the pattern of the magnetic field lines. What is iron fields?
Yeah.
Okay.
Iron fillings are very small pieces of the iron. They look like light powder, and they are very often used in science demonstration to show the direct of magnetic field. And the magnetic field science is a ferromagnetic material, and the iron fillings use it in the study of magnetic field and the S reagent in chemistry.
Okay, thank you, Alia. Sit down, please. Okay, next to presentation, we write your copybooks, and magnetic field at some point in space can be defined in terms of the magnetic force. The magnetic force exerted on a charged particle moves with a velocity. As some for now, there are no gravitation or electric field present. What is most is moving particle moving with a velocity. This is great. Lorentz force. Their properties can be summed in a vector equal FB equal Q multiplied velocity multiplied V, where FB is the magnetic force, V charge, V velocity, and B magnetic fields. Because velocity and magnetic fields between degree angle theta, force and velocity angle perpendicular. Okay, force and magnetic field perpendicular to. Okay. Direction, right hand rule. Please, right hand. Okay. Tram is in the direction velocity. Velocity what? Particle, change particle. Okay. Fingers are in the magnetic field. Okay. And palm is force. Force. Okay. Right hand rule. Okay. Move about magnet of F. Please write into your copybooks. Okay. The magnitude of the magnetic force on a charged particle. is FB equal Q multiplied V multiplied B multiplied sinus theta. This is theta is the small angle between velocity and magnetic fields. Okay, FB is 0 when the field and velocity are parallel and all antiparallel. Because theta equal 0 or theta equal 180. Okay, and FB is a maximum when the field and velocity is a perpendicular. Because theta equal 90. Okay, excellent. Did you record in your copybooks? And we see one video.
Force on an electric charge moving in a magnetic field. Lorentz force. The current I flowing through a conductor of cross-sectional area A is given by I equals to NA VdQ, where Q stands for charge on the positively charged particle. N stands for number of free charge carriers per unit volume of the conductor. Vd stands for drift velocity. Therefore, I dl bar equals to Qn A Vd dl bar equals to Qn A Vd bar dl. Since Vd and dl are in the same direction, when this conductor is placed in a magnetic field of intensity, B bar, the force acting on it is dF bar equals to IDL bar cross B bar equals to Qn ADL VD bar B bar. But N ADL stands for total number of charged particles on the current element. Therefore, the magnetic force acting on a charged particle of charge Q is given by Fm bar equals to dF bar by N ADL equals to Qn ADL into Vd bar cross B bar by N ADL. The magnetic force acting on a charge moving through a magnetic field is perpendicular to the velocity of the particle. Work done by this force is zero, and hence the kinetic energy of the particle remains constant. Only the direction of velocity goes on changing at every instant. If an electric field E bar is also present along with B bar, the resultant force acting on the charged particle will be F bar equals to Fe bar plus Fm bar equals to Q into E bar plus Vd cross B bar. This force is known as Lorentz force.
Okay. What do you think about it? Okay, Mr.
In this video says about force of electric charge moving on magnetic fields, about Lorentz force, and we know Lorentz force formulated force equal Q multiply B multiply V, where Q charge of positively particle, and B magnetic field, and B velocity of particles. And we know in System International the unit of Lorentz force is Newton. And the work done by this force is zero, and the kinetic energy of particle remain constant.
Okay, thank you.
This video was informative.
Okay, thank you. Sit down, please. Next two. And we electric force and magnetic force. You know what electric force acting at a distance throws electric field. Yes? Yes. Magnetic force acting at a distance throws magnetic field. Okay. Vector field B. Vector field B. B. Okay. Source electric charge. This is moving electric charge. Moving electric charge. Yes. O. Current. Current. O. Magnetic substance such as. Okay. This is positive charge or negative charge. This is magnetic field. North pole and the south pole. Yes. Opposite charge. Repeat. Okay. And magnetic fields. Repeat. Yes. And electric field lines. B. This is B. Yes. This is electric and magnetic fields. Okay. And unit of magnetic field. The C unit of magnetic field is the Tesla. Tesla equal per meter square equal Newton per Coulomb multiplied meter per second and Newton per ampere multiplied meter. And known C commonly used unit is a Gauss, because 1 Tesla equal 2 degree Gauss. Yes. Okay. Do you understand? Yes. Yes. Okay. And go to the fourth question, our plan. And magnetic force on a current carries conductor. A force is exerted on a current carries where placed in a magnetic field. The current is a collection of many giant particles is motion. The direction of the force is given by the right hand rule. Okay. Look at the blackboard. This is 3 cases. Okay. First case. In this case, there is not current, so there is no force. No current, and throws the wire remain vertical. Yes? Yes. Yes. Okay. Second cases, the magnetic field is into the page. The current is up page. The force in the left. Okay. The magnetic field is into the page 2. Okay. The current is down page. The force in the right. Okay. This is ampere law. In terms of the current, this become F B equal I multiplied L multiplied B. This is I is the current. Okay, L vector point is the direction of the current. It is magnitude is the length of the segment, and D is this magnetic field. Okay, and we
force on a moving charge in a magnetic field
and forces between two parallel current-carrying wires. In this module you learn that a moving charge in a magnetic field and two parallel current-carrying wires experience a force. You may know that a current-carrying wire experiences a force when it is placed in a magnetic field. You may also know that the current is the flow of electric charges, that is, free electrons in a wire. Here you examine the effects of a moving electric charge in a magnetic field. Take a look at this figure. The crosses represent a part of the magnetic field. The direction of the magnetic field is into the plane of the paper, away from you. When a beam of positive charge, for example protons, enter the magnetic field region, the beam is deflected upwards in a circular path. This deflection of the beam of positive charges is because the moving charges experience a force perpendicular to their direction of motion. The direction of this force can also be predicted by Fleming's left-hand rule. You can assume current to be in the direction of the beam of positive charges. However, if you have a beam of electrons or negative charges, you follow the conventional current direction, which is opposite to that of electron flow. This figure shows that a negatively charged particle is deflected downwards in the same magnetic field. This figure here shows that the beam of positive charges of protons enters the region of a magnetic field, which is directed out of the plane of the paper towards you. The beam is now deflected downwards. You will next learn about the forces between two parallel current-carrying wires. When two current-carrying wires are placed parallel to each other, you would expect a force to act on each wire. This figure demonstrates the forces that exist between two parallel current-carrying strips of aluminium. When the current in each of the conductor flows in the opposite direction, the strips repel. However, when both currents are in the same direction, they attract each other. So you can summarize the forces between two parallel current carrying in opposite directions and similar directions respectively. This magnetic field pattern of a current carrying wire can be found by applying the right-hand grip rule. In this module you learn the topic. When a moving charge enters the magnetic field, the beam experiences an upward or downward deflection of force, depending on whether the charge is positive or negative. When two current-carrying wires are placed parallel to each other, each of the wires experiences a force. When current flows in the opposite direction in two wires, repulsion occurs. When current flows in the same direction in the two wires, attraction occurs.
Okay, what is your think about video? Okay, Danielle?
Force on a moving charge in a magnetic field and forces between two parallel current carrying wires. In these modules, we will learn that a moving charge in a magnetic field and forces experiences a force.
Okay.
And we now write Fleming right-hand rule. The trump is this force direction, this finger direction of magnetic field,
Okay.
and this finger direction of current.
Yes.
And when two current carrying wires opposite direction each other, each of the wires experiences a force. And when the current flows in the opposite direction, in the wires, repulsion occurs, when the current flows in the same direction in the wires,
Okay.
attract occurs.
All right. Excellent. Down, please. Okay, and you a lot of exercise by our topics lab. And question 1. Okay, Bobby? Please read. Is question 1?
Units of magnetic field might be magnetic field equation. This is B equal force divided charge multiplied velocity, and this is unit of magnetic field Tesla. Tesla equal Newton divided Coulomb multiplied unit of velocity, and this is force equal mR. This is kilogram, and this is meter divided second square, and this is kilogram multiplied meter multiplied second. This is second square multiplied coulomb and multiplied meter. This is a decrease meter and second, and then unit of magnetic field kilogram divided coulomb multiplied second.
And
Solution this question. Answer this question D.
okay, all right? Yes. You do. Okay. Excellent. First question. What is Aida?
First question in the formula force equal change multiplied velocity change magnetic field. This direction of Lorentz force determined by the rules and by the left arm. The direction of velocity is the direction of magnetic field and the direction of force. Answer the first question A. Force must be perpendicular to both velocity and the weight. The direction of Lorentz force.
Okay, thank you. Question 3. What?
Answer this question 0. Because an electron is moving north in a region where the magnetic field is south, the magnetic force acting on the electron is 0.
Okay.
Answer this question 0. A.
Ada. Okay. All right?
Yes.
Yes, okay. And question 4 is the tasks. Okay. Please read. Aslan, read the task.
An electron charge equal minus 1/6 multiplied 10 minus 18 coulomb is moving at 3 multiplied 1.5 degree meter per second in the positive x direction. A magnetic field of 0.8 Tesla is in the positive z direction. The magnetic force of the electron is
Okay. This is data. Okay. Who? Equal. Given.
given electron and electron equal electric charge. And velocity, it's equal meter per second, and magnetic field equal 0.8 Tesla. We must verify to the force, magnetic force.
Okay.
We know the formula of Equal is 4 multiplied 1 minus 14
Okay.
Newton.
Newton.
And in this task, moving is the positive x direction, and magnetic field it is in the positive z direction. Then force perpendicular to the magnetic field. Then solution is the 4 multiplied 1 minus 14 Newton in the positive y direction.
Okay. Answer?
D.
D, then? Yes. Okay.
E, x, and z.
Okay. Thank you. All right?
Yes.
Yeah. Is this equal? Okay. Another. Read, please. Is this?
H1 instant and electron charge minus 1.6 multiplied 10 minus 19 degree Coulomb is moving in the xy plane. The components of its velocity being velocity vx is equal 5 multiplied 10 5 degree meter per second, and Vy is equal 3 multiplied 10 5 degree meter per second. A magnetic field of 0.8 Tesla is in the positive x direction. At that instant, the magnitude of the magnetic force on the electrons is.
Okay. Please write on the blackboard. And please, you in intro, write your quadruples. This is exercise, because this exercise in control walk going through.
The angle between the velocity and magnetic field is perpendicular 19 degree. So we take the significant velocity y direction.
Okay.
And the force is equal 3.85 multiplied 10 minus 14 degree Newton.
Okay, thank you. Answer B, да? Okay, thank you. Sit down, please, Ina and Dana. Together, billions of tiny atomic magnets act as a big magnet. The Earth has a magnetic field, a rule for field direction, And Lorentz force, magnetic field B, is defined in terms of the force acting on a test particle with charge Q moving through the field with a velocity. Fb equal Q multiplied velocity multiplied magnetic field. And you now see unit of magnetic fields Tesla. 1 Tesla equal 1 Newton per Coulomb multiplied meter per second equal 1 Newton per meter. And you please homework repeat write in either your copybooks. Is this exercise? I see. Next, our students.